Another interesting effect that can occur with high-speed flows is vortex shedding. So vortices are regions of spinning fluid, and we'll talk about those more a little bit later. But one thing that can happen when you increase the Reynolds number past an object like this, imagine this is again a circular cylinder, so going long in and out of the page, is it can start to do what's called vortex shedding. So if you get in the region of Reynolds number between 40, which is actually before it's turbulent, all the way up to 10,000. In this region, you'll see that it will exhibit vortex shedding. So what this means is basically regions of spinning fluid come flying off the edges. Interestingly, they come off in alternating sequences. So I've tried to draw that here. So this is point A, creating some vortex generation, and that vortex is shed, and it's shed this one and this one. And then in between these two, you see a vortex shed by point B. So the vortex shedding occurs at a regular frequency, and it alternates between sides. So it'll shed from A, then shed from B, then shed from A, then shed from B, and a very predictable frequency. So it's a fascinating phenomenon. It's actually the reason the Tacoma Narrows Bridge collapsed. If you know this video of the Tacoma Narrows Bridge, you can look it up. The bridge starts to oscillate, and it's at its resonant frequency, and that causes the bridge to oscillate out of control and eventually shake itself to death. And for a long time, no one really knew what was causing the initial forcing that would cause it to oscillate. And they figured out that it was, in fact, vortex shedding. So wind blowing at a very particular speed was causing vortices to shed, and every time it shed a vortex, that would vibrate the bridge a little bit, and eventually that small amount of perturbation caused the whole bridge to collapse. So anyway, the frequency at which it sheds these vortex depends only on U infinity and D. So if you're at higher Reynolds numbers, that is not at the really low Reynolds numbers of vortex shedding, but above them in the turbulent regime, at high RED, the shedding frequency, which we're going to call F, depends only on U infinity and on D. So it doesn't depend on anything but the velocity and the diameter of the object. And it's characterized by this Struhel number. So when people want to talk about the shedding frequency, they use the Struhel number. It's abbreviated ST, and it's defined as the frequency times the diameter divided by U infinity. So this is going to be 1 over seconds. That, of course, is meters. So you have meters or seconds over meters per second. So the Struhel number, like all of our wonderful numbers that we use to give the name number to, is dimensionless. In the region of Reynolds number 300 to 10,000, for Reynolds number greater than 300 based on D and less than 10,000, the Struhel number is pretty much constant, so it's 0.21. So a very predictable vortex shedding frequency, because the frequency, of course, looking back at the definition of the Struhel number, the frequency is therefore proportional to, D, it's ST. Let's start all over. Frequency is equal to ST times U infinity over D. So it's proportional to the velocity, and it's inversely proportional to the diameter of the object. And the Struhel number is holding constant at about 2.21 over this large Reynolds number range. So it's basically going to increase in frequency as your velocity increases. So we're not going to do a lot with how this happens or anything. It's just something interesting to know, something that you might need to know if you're dealing with high-speed flows, that you could have this effect of vortex shedding coming off the object, and you can predict its frequency very simply based on this relationship.